Hi, my name is Dippon. I'm with Keysight Technologies in Germany. And in this video, I would like to present signal generation and signal analysis for up to 140 GBaud, specifically for coherent optical applications. Let me first explain the hardware setup that we have in front of us. On the generation side, we have the new Keysight M8199A arbitrary waveform generator. It runs at up to 128 gigasamples per second on 4 channels, or in interleaved mode up to 256 gigasamples per second on 2 channels. That's our configuration we have today. The box that you can see in front of the AWG is doing the interleaving, and on the front of that you can see the differential outputs of the AWG. On the bottom of the AWG, or below the AWG, is a clock module that generates the sample clock for the AWG, and you can see the clock cable running over to the AWG in addition to a synchronization cable. Now, as we go out of the AWG, you can see the 2 boxes on the table. Those are remote heads that amplify the signal and allow you to get closer to the device under test. Now, in this particular setup, we just have a back-to-back electrical setup where we take the outputs of the remote heads and connect them directly to a 110 gigahertz UXR oscilloscope. So in this configuration, we can use the 2 channels of the AWG with a bandwidth of about 70 gigahertz to generate 1 IQ pair of signals up to round about 140 GBaud. Now, for dual polarization experiments, we can add a second AWG module that is synchronized with the first one, and that allows us to generate a second pair of IQ signals so that we can generate a total of 4 signals for dual polarization IQ. In terms of software, we are using the IQ Tools software on the generation side to both generate the waveform signals for the AWG and also to run what we call an in-system calibration to evaluate the frequency and phase response of the system and pre-distort the signals accordingly so that we can optimize the signal. On the analysis, we're using the VSA software from Keysight, which in this case is configured to demodulate a 16 QAM signal running at 140 GBaud. You can see the constellation on the top left, and then an eye diagram, and also the spectrum on the bottom left. In this particular configuration, it looks like we're achieving an EVM of about 7% for the electrical back-to-back connection.
Hello, my name is Klaus Engenhardt, and I'm the technology lead for Keysight's Coherent Optical Test Portfolio. I would like to take this opportunity to give you a brief overview of how this all-electrical setup right here can be extended for applications in the coherent optical domain, either for full system transmission tests or for evaluation of coherent transmitter or receive subassemblies used for IQ modulation or demodulation. Let's start with complex optical modulation analysis. The essential tool for this application is the Optical Modulation Analyzer, or OMA for short. An OMA basically consists of 3 elements: a real-time oscilloscope for electrical digitization of the acquired waveforms, a coherent optical front-end receiver, and signal processing and analysis software that provides detailed insight into the physical layer characteristics of a complex modulated optical signal, including display of the constellation diagram and signal characteristics such as error vector magnitude and other parametric measurements. The latest release of the OMA analysis software includes enhanced DSP algorithms for stable demodulation of ultra-high baud rate signals and also signals with low signal-to-noise ratio. Next, I want to talk about generating optical complex modulated signals. A powerful tool in combination with the new AWG is the Optical Modulation Generator software, 81195A. It can easily synthesize multi-channel electrical waveforms for the AWG to drive dual polarization IQ optical modulators. The base version is free of charge and contains a number of convenient features, such as a selection of predefined modulation formats, symbol rates, data patterns, and pulse shaping types. In addition, it can automatically compensate for signal degrading effects such as cable loss or the inherent frequency response imperfections of the AWG output stages. This allows to always achieve optimum signal performance. Furthermore, it's possible to digitally emulate optical signal impairments such as phase noise, polarization rotation, or polarization mode dispersion with this tool. The most recent release version supports control of the new M8199A AWG in 4-channel operation at 128 gigasample per second, and the next release later this year will also support 4-channel operation at the full 256 gigasample per second in interleaving mode. And that was a brief overview over coherent optical signal generation and analysis for terabit class signals. Thank you for your interest, and goodbye.